Hi everyone, I'm back with this problem that we were working on in class today. I pulled a new one. I know this one is going to work now and we have some explanation to go through. So we're just going to go through it real quick. So this problem comes from your Alex homework for section 5, and again it's essentially asking at what point will this reaction be spontaneous, because what we're going to find is that E cell is going to be negative, which we know means non-spontaneous. However, for our galvanic cell to work and for us to have electricity flowing, we have to have a spontaneous reaction. But since we're at non-standard state, we're just looking for E cell to be spontaneous. So we're looking for the minimum ratio that our concentrations of our solutions need to be in order to make that E cell spontaneous. Okay, so now what's a little deceiving in this problem is the comparison of the picture to the reaction that we're being shown. So the reaction shows that we have a nickel anode and a copper anode, and based on their reaction or reduction potentials, that would be where we would expect them to exist. However, since we're at non-standard state, the reaction that we're referring to, which is below this picture, so make sure you're always looking at this reaction below it, because that's really going to tell you what's being oxidized and what's being reduced. So if we look at our reaction here, I'm just going to zoom in a little bit, we see that copper is going to copper 2+, and nickel 2+ is going to nickel. This would suggest that copper is being oxidized and nickel is being reduced, right? Because our reduction has our electrons in the reactant side, whereas our oxidation has it in the product side. So we would expect this to happen at the anode and this to happen at the cathode. However, that's not what this picture is showing. So that's why this picture is a little bit deceiving, because it's saying this is traditional, like standard state, but this is this reaction down here is our non-standard state reaction that we actually want to happen. So we're saying, what do the concentrations of our ions need to be in order for this reaction to happen in this galvanic cell? So essentially, how am I going to get my electrons to reverse in this galvanic cell? Okay, so how do I want them to go backwards? Okay, so if we then go back to our definition here, we know that E cell, I mentioned that it's going to be negative, okay, and that's because of this reaction here. So if we do E cell naught is cathode minus anode, we are going to get that the cathode is nickel, negative 0.26 minus 0.34. We can see that that's going to be negative. So if we take out our calculators and do that, let's see, negative 0.26 minus 0.34, we get an E cell naught that is going to be negative 0.6 volts. I'm going to throw an extra 0 on there for sig fig purposes. So essentially what this problem is saying is this reaction down here, as it's written, is non-spontaneous. I am not going to have copper ions from here moving to my nickel area over there from one cell to the other, one half cell to the other, okay? I'm not going to have that happen spontaneously. So what I want to do is I want to adjust my concentrations of my solutions in order to allow that to happen, to essentially have my cathode act like my anode and my anode to act like my cathode and reverse the flow of the electrons. So what we need to find is the ratio at which those ions need to be in. Now, as we talked about in class, Q is the ratio of those ions. Q is the product ions divided by the reactant ion and their concentrations. And again, if they have coefficients, you're raising them to those coefficients. Okay, so what we need to find is Q. So if we try to plug in our values here, we know E cell is this negative value, 0.60 volts, minus 0.0257 divided by 2. It's 2 electrons that are being transferred, ln of Q. Now, if we're trying to find Q, I also need a value for E cell at non-standard state. So, again, the question is asking, what is the ratio where the following reaction, the reaction down here, okay, remember to look down there in your problem when you do this on your homework, okay? When does that reaction become spontaneous? When will the electrons flow the other way? When will they reverse? So we have to remember, positive E cell is spontaneous, negative is non-spontaneous. So what number do they have to go through when I go from a non-spontaneous negative E cell to a positive spontaneous E cell? Think about that for a second. What number is my turning point between non-spontaneous and spontaneous values? Did you remember that we've talked about that before? And we said that 0 is our value when we're switching from non-spontaneous to spontaneous. We talked about that back in chapter 15, I believe. Maybe even in chapter 16 when we started talking about equilibrium and we started swapping our equilibrium back. But we said that 0 is going to be our kind of changing value from non-spontaneous to spontaneous. The number where I go from a negative to a positive. That is going to be 0. So our definition of E cell at non-standard state is going to be 0. So the minimum concentration that these are going to be when I become spontaneous at 0 volts. So when does that start to switch over? So now this becomes a lot easier of a problem to solve for because of that 0. So we can see that we're going to move that negative 0.06. We're going to add that, or that 0.6. We're going to add that to the other side. So we get positive 0.60 is equal to 0.0257 divided by 2 ln of Q. I can simplify that 0.0257, 0.0257 divided by 2. So we get that 0.60 is equal to 0.01285 ln of Q. I'm again trying to solve for Q, so I'm going to do 0.6 divided by that 0.01285. So I get that the ln of Q is equal to 46.692 and some change. Now the reversal of a natural log is e to the. So when we're doing standard state conditions, when we want to get rid of a base 10 log, we use 10 raised to the whatever that value is. Here we're doing natural log, so the reversal of a natural log is e. So we're going to do that Q is equal to e raised to the 46.692 and some change. So we do that in our calculator, second E, answer, I get a Q value of 1.898 and so on, times 10 to the 20. Let's see, do we have any numbers to go off of here? No, let's call it, 2 sig figs. We know our Alex homework is going to tell us, but let's just be proper there. So that is the ratio at which these ions need to be in order for the reaction to be spontaneous and move the electrons to move from our cathode to our anode. Okay, so that is the concentration that we are going to need, the ratio at which those ions need to be in. Again, I apologize for having the wrong problem in class today. The wrong problem had the incorrect equation below it. It had the proper equation where E cell wasn't negative, but I wanted to show you the negative representation there. So again, I apologize for that. Take a look at this problem in full if you needed to see that. You're going to see this on your homework as well. So that's why I wanted to make this video so you could watch it before our class on Friday. And that way you had some time to ask some questions before your quiz and homework are due.